Okay, I hope I'm live and I'm audible too. Uh, I will just check real quick. Yeah, I'm audible, so I will be starting the live cast. Okay, so I'm using the slides of Professor Dr. Mohammad Faisal sir. Uh, He's currently teaching in Department of Triple E, Bangladesh University of Engineering and Technology. Uh, and we will just quickly go through the slides while I study this. And as the live stream goes, basically, we will go through the all 41 slides. So switching system, first, let's quickly go through the table of content and the topics. It contains space division and time division switching, and we have crossbar switch, we have operation of crossbar switch, and we have principles of common control, and under this we have event monitoring, call processing, charging, operation, and maintenance, and yeah. Okay, so principles of common control. Under this topic, we have event monitoring, call processing, charging, operation, and maintenance. And then we have decisions made on following subscriber, which specifies class of service information. We have classification of class of service information of the subscriber. One is called barring, one is called priority, call charging, origin-based routing, no dialing calls. And then we have stored program control, which is SPC. And up next, we will have centralized SPC and distributed SPC. And we will go through more details of centralized SPC and later uh, discrete SPC. So we have a synchronous duplex operation, and then we will go through the load sharing configuration for the centralized one. Control in centralized SPC, that's on the topic, and then we'll finally go through the distributed SPC. Uh, yeah, and then that's it. So we have level 3 processing, level 2 processing, and level 1 processing. So this was the table of content. Now we proceed to the switching systems, space division and time division switching. So crossbar switching, the Stroger switching system, which is the uh, I guess this is the crossbar switching system's another name. So Stroger switching system has been the basis of telephone communication, telephone switching for almost 70 years since introduction in 1889. However, major disadvantage of Stroger system is its dependence on moving parts and contacts which are subject to wear and tear. Such mechanical systems require regular maintenance and adjustment. For this purpose, they must be located. So this is the developed version. Crossbar switch is the developed one. This is older, and then got rid of all the mechanical hassles and we found the crossbar switch. The telephone network spread to remote areas. It becomes necessary to devise switching systems that would require less maintenance, little adjustment after installation, and less maintenance and little adjustment is the two requirements. Efforts in this direction led to the invention of crossbar switching systems. So a little summary of this slide, we came to know we had a Stroger switching system, but it's old and it requires lots of mechanical maintenance, and it's tough to uh, navigate since the moving parts and contacts. So for the improvement, crossbar, which certainly meets up the following requirements. One is less maintenance. And one is the readjustments for the distant network, obviously. Okay, a crossbar switch is an electromechanical switch based on the same principle of coordinate switchboard. So crossbar switch is principle maintains the principle of the coordinate switchboard. Coordinate switching is manual, but crossbar switching is electromechanical. It's not manual; it's electromechanical. Here, number of moving parts are less, uh, less maintenance since the moving parts are less, so this is why it's less maintenance. Common control concept is used. The switching devices are provided at the intersection of vertical and horizontal circuits. So we will have some vertical and horizontal circuits and switching intersection. This will be our switching device. I denote it with SD. The intersection and switches are called cross points. So this is the cross point. The complete array is called matrix. So this is the matrix. So the summary is it follows the coordinate switchboard concept, and it's though it's manual, but the crossbar switchboard is electromechanical, electromechanical, and in previous slide we mentioned the less maintenance part. Since the moving part is less for the crossbar switches, it suddenly follows this requirement. So this is a coordinate switching for figure 4.1. So this is the coordinate switching part. So what happens is this is certainly 1 to 12, and this all the vertical and horizontal circuits. The links are adjusted. Written here. So we have different parts. One is this one, A, which is uh, a armature-like thing. So how it's drawn. So this is the cross section, right? And then we put uh, this thing. Okay, and then okay, and so this is A, this is B. So in the B, we know this is the crossbar switch, and we put three dots, and we have flags into switch the rest to, and one is extended. Okay, so this is another where this is put and this is the switch. But this is the switch. So another, this is a diode, and then I'm drawing this part right. So this is a diode and this is a switch box, and rest is just a switch and a arrow. Okay, so all these are connected to the subs and the substations and the operator's telephone. So this is the summary of the slide, and we will proceed. So the basic idea of crossbar switching is to provide a matrix of n into m sets containing with only n plus m activators or less to select one of the nmn sets of the contacts. So we will have n and m, n into m selector, and n plus m activators will select amongst this n into m. For 3 into 3 arrangements, so 3 plus 3, 6 will be the number of activators. 9 cross points are required. There is an array of horizontal and vertical wire, arrays of horizontal and vertical wires shown by solid lines. A set of vertical and horizontal contact points are connected to these wires. So these are the contact points, right? The contact points form pairs, which pair consisting of bank of 3 or 4 horizontal and a bank of vertical contact points. A contact point pair acts as a cross point switch and remains separated open when not in use. Okay, so okay, the contact points are mechanically mounted on a set of so the contact points is mechanically on set of horizontal and vertical bars as dashed lines. The bars in turn are attached to a set of electromagnets. So the bars are attached. So what happens first? The bar is connected to mechanically, the contact points are connected to the bar, and bar is connected to a EM, the EM. So this is something like this. We can assume, right? A contact point pair acts as a cross point switch. So this is the contact point is the cross point switch itself, and remains separated open when it's not used. So as we can see in the previous, so when it's not used, its switch remains open. And this was showing here the contact point is attached to the bar and it's connected to a electromagnet. So I will be leaving for a 2 minute short break and coming soon. Okay, I'm back from a break. I'm back from a break. So we will continue the slides and yeah, I was here. Page down. When an electromagnet, say in the horizontal direction, so we are considering this. This will be the total matrix, and in the horizontal condition is energized. So in this horizontal direction, so it's energized in this direction. The bar attracted to it slightly rotates such so first let's assume this. Okay, so let's assume something like so this. Okay, and the energy is provided, and this is slightly tilted, rotates in such a way that contact points move closer to the facing contacts. Okay, and this happens, and the switching contacts, say it's this and this comes here, and the contact but do not actually make contact, so it comes closer. So if we see the this part in a zoomed view, so what we will get, this will be the contact point, and due to the tilt of the bar, it comes something like this, something it will be something this, but we will still have the gap. Okay. Now, if the an electromagnet is in vertical direction, it's energized, the corresponding bar rotates, causing the contact points. Okay. And then similarly, this will happen and it will also appear, and this comes towards it, and it the if the both horizontal and vertical point contact points both the EM of horizontal and vertical aligns, then the cross point is finally energized and uh, establishes an connection, right? So this is it for this slide. As an example, if the okay, so this is the bar that we were talking about. If we look closely, it's 3 into 3 switching, obviously 1, 2, 3, 4, and for the each switches for the each bars en, so the magnets are connected just in the centers, and the wires are attached and just in the horizontal and vertical direction, and for each switch the crossbars are connected like in this manner. So this is one, this is 2, and this is something like this. Okay. As an example, if electromagnets M2 and M3 prime are energized, a contact is established. So M2 and so this is the contact is established at 6 such that the subscriber B, so subscriber B is connected to the subscriber C. Now why so? Uh, Such that the subscriber B is connected to subscriber C, because the line B is B I can understand, but C actually actually I feel the line B, right? The line B represents the row for 2. So 2 is the row, and the column it finally propagates to C. Okay. Actually, I feel the subscriber C is customized. We can do with subscriber A or B as well. It's the direction that matters of the connection point. This is, I'm assuming, I'm not sure actually. So this, let's go through the process of connection. First, energize the horizontal bar. So this is the horizontal bar M2. So if this is step 1, this is first. Energize the vertical bars. This is step 2. De-energize the horizontal bar. Then okay, I will denote the de-energization in with red and energization with orange, right? And the vertical bar remains operated during the call. So this continues, right? When cross point is to be released, end of the call, when this bar is okay, and when it's the call is ended, the fourth bar is de-energized as well. So for establishment, the both electromagnet needs to be energized, but to continue the call, only a single magnet energization is enough, or opposite sequence may be followed. It's vice versa. We don't have a strict recommendation for this. Okay, so single switching stage, it will be a single switching stage with 81 cross points, 9 into 9. The limitation of crossbar switching is that it is uneconomical for large networks. 9 into 9 matrix, 81 switches, 9 paths between 9 inlets, outlets. It is single stage switching. Using multi-stage switching, required number of cross points can be reduced. So if we switch with multi-stage, then the required number of switching may be introduced. So this is the intro of multi-stage switching. So we have 9 inlets, 9 outlets. These are pretty clear, and we will group it into 3 into 3. So what happens is, this is these are three chunks of 3 into 9, right? So where the 2 into 9 into 3 comes in handy, that so these are 9 links, 9 inlets, 9 outlets, which is chunked into 3 sections. So these will be 3, and for 3 sections. So these 9 links are connected to 3 sections. These 9 links are each connected to the wire of threes. So 3 into 9. So NK is certainly 2. This is for, one is for input and one is for output, the cross point definition. If we see, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, and it repeats for 3 times. So this is the cross point total calculation, right? So this is input and output. N is the number of lines that's provided, and K is the chunks, number of chunks. So number of lines, number of chunks. So this is 54 cross points. So we came from single stage 81 to multi-stage 54. So 100 links, 10 into 10, as we should know, for the single point it would be 10 to the power 4, but now we have 10 chunks, so 10 into 100, it's with 2, so this is 2000. So it reduced 8000 cross points. In practical exchanges, we need to provide only as many paths through the switching network as the number of calls. So the path number, so number of paths should be essentially the max number of calls. We don't require more than this. So this has to be considered when we are uh, designing this paths and the stage communications. So principles of common control: the Stroger exchanges director subsystem performs the functions of exchange. Okay, exchanges, director in Stroger exchanges, director subsystems performs the functions of exchange identification and subscriber. So director subsystem is a thing which performs two things. One is exchange identification and two is subscriber identification. But in crossbar systems, same thing is performed with common control switching, which is CCS system is used. A number will consist of two parts. A number will consist of two parts. So what this is referring to, say this is some number. So this will be exchange identifier, and this will be subscriber identifier. So exchange must have the capability of receiving and storing the digits dialed, translating and exchange identifier. So it has several functions. One is capability of receiving and storing the digit dials, translating the exchange identifier into routing digits. So which path it will take, that must be identified, and the transmitting, the routing and the subscriber line to, and finally allocating the subscriber line which will it route to for the receiver. Okay, so these are the three functions for the CCS exchange ID. So now the subscriber ID. As soon as okay, we will conclude here, and I will come from a short break. As soon as the translated digits are transmitted, the director is free to process another call. So translated digits from the exchange ID, right? So the transmitter, the director is free to process another call, and is so the director subsystems, that's it's mentioning from the Stroger switching, is not involved in maintaining the circuit for the conversation. Call processing takes place independent of the switching matrix part. So the switching matrix part, call processing is not dependent on this. A user is assigned a local number, which is, now we are talking about subscriber ID, which is independent of the physical line number used to establish a connection to him. The logical address is translated to actual physical. So this ID is basically a translation of the physical address, the IP address of the device. Let's just assume this for our feasibility of, of the system currently. For connection establishment by an address translation mechanism. All the above are fundamental features of a common control system, CCS. A functional block diagram of a common control system is shown in figure. So where's my figure? Okay, so this is the common control system. In summary, we will study it later. The control functions in a switching system may be placed under four broad categories. So control functions, the switching systems we will study after a short break. Bye.